Welcome back to Calculus 1. This is the second part of our lecture on derivatives and the shape of a graph. In the first part, we explored what the first derivative tells us about the function. The first derivative tells us where the function is increasing and decreasing, and it also gives us a test for local maxes and local mins, the first derivative test. In this lecture, we're going to explore what the second derivative tells us about a function, and then also arrive at another test for local maxes and local mins using the second derivative. Okay, so the question is right now just what the second derivative tells us about the function, and the answer is a concept in calculus called concavity. This is the technical term for basically curvature of a graph, whether it's kind of curved upwards or curved downwards. We're going to make that a little more precise. Okay, so we have two standard examples here of each. We have a shape of a graph here for which we're going to call a concave up shape, and then another shape that's called concave down. So just imagine each of these as a small part of a much larger graph of a function. So each of these small parts or pieces on the left is concave up, on the right is concave down. Now we're going to kind of explore what the second derivative tells us, but we have to tie this in back to the first derivative. And if we think, what does the first derivative tell us? We learned that it tells us where a function is increasing or decreasing, but we also know a first derivative represents a slope of a tangent line. So let's take that perspective for the time being. So if we look at the concave up shape, we can see a particular pattern in the signs of the first derivative. So if we go left to right, on the left there, the first derivative is negative. That's because the slope of the tangent line is negative. Right there at the local minimum, the derivative equals 0, since that's a local min, a critical point. And then just to the right, the derivative is now positive, since the slopes of the tangent lines are positive there. So we can see here the derivatives going left to right change sign, going from negative, 0 to positive. For the concave down part, it's pretty much the opposite. It's reversed. On the left, the slopes of the tangent lines are positive, so the derivative is positive. Then at the local max there, the derivative equals 0, since it's a critical point. And then just to the right, the derivative is now negative, since the slope of the tangent line is negative there. All right, now what we can notice is on the left, the concave up shape, if a quantity goes from negative 0 to positive, we can say that quantity is increasing. Negative, 0 to positive, those values are getting bigger. Now let's just be clear what is getting bigger or what is increasing. The values of the slopes. So keep in mind, derivatives correspond to slopes of tangent lines. So the slopes are increasing. The slopes go from negative to 0 to positive. On the concave down graph or shape, it's the opposite. The derivatives are decreasing, going from positive 0 to negative. So on the right side, for the concave down part, the slopes are decreasing. Now this is going to be where we tie it into second derivatives, since there's kind of a notion of a derivative in each part. All right, if we take a look at the left with the concave up shape, we arrived at the statement that the slopes are increasing. Now, what determines slopes? The quantity that does that is the first derivative. Now, what determines if a quantity is increasing? The derivative of that quantity is positive. Now, if we put that together, the quantity involves a derivative, the first derivative. Increasing, it comes from the derivative of that quantity. So what we're talking about here is the derivative of the derivative. And that's what we call or define the second derivative, f double prime. So what we see here is for a concave up shape or graph, the second derivative is positive. That's because the slopes are increasing. That means the derivative of f prime has to be positive. And that's what we state here as f double prime being greater than 0. It's pretty much the same thing on the right side with the concave down shape, just kind of switch. For a decreasing quantity, its derivative is now negative. So similarly, we arrive at this statement for the concave down shape that the second derivative, again, the derivative of the derivative, is going to be negative. And this gives us our first relationship, what we're going to call the concavity test. And it's going to be what we apply to some following examples. And it's pretty simple. It basically says if the second derivative of a function is positive on an interval, then the graph of the function is concave up. And if the second derivative is negative on an interval, then the graph of the function is concave down. So positive second derivative, it's curved upwards. Negative second derivative, curved downwards. Now, once we get to graphing, we're going to kind of want to combine this all together from a concavity with the first derivative. And there's a few different possibilities. We could have a single connected piece there for the concave up piece. Kind of looks like the graph of x squared. But it could be kind of split in the middle and having each of those two individual parts. So at the bottom there, all three of those are concave up graphs or curves. You could have the continuous connected piece that looks like the graph of x squared, or you could have the individual parts where you split that in half. Same goes for concave down. You could have the full piece, which looks like the graph of negative x squared, or you could split that in the middle and have either the left or right half for those being concave down graphs or curves. All right, this is going to be the start of how we pull this together with the first derivative to sketch a graph. We're going to save that for part 3 of this lecture. Let's go ahead and get to some examples. Since the concavity test referred to intervals, we might be thinking, how do we first find these intervals? And that's where we're going to introduce a concept similar to a critical point, but it's different. We're going to introduce something called an inflection point. So just bear with me. We'll relate this back to the intervals we referenced earlier a few moments ago with the concavity test. We have to address how do we find those intervals. That's where we're going. We're starting first with an inflection point. Okay, the definition is very simple. We're going to say a point where the concavity of a function changes either from positive to negative or negative to positive, a point where the concavity goes from concave up to concave down, or vice versa, is called an inflection point. And just be careful here. These are similar in the role they play to the first derivative, but they're a little bit different. Notice the definition here says nothing about the second derivative equaling 0 or the second derivative being undefined, which is similar to how we defined critical points. Let's take a look at what an inflection point looks like. So we have to keep in mind the definition says something about the concavity changing. Now let's take a look at a concave down shape and a concave up shape. So we have the two individual pieces there. How we can get an inflection point is basically attaching or gluing those two pieces together. So if you kind of take the right endpoint of the concave down part and connect it with the left endpoint of the concave up shape, you get this nice kind of curvy graph. Right in the middle there is where the concavity changes from concave down to concave up. That's what an inflection point looks like. Now there's a simple example. The graph of y equals x cubed has an inflection point. We brought this up earlier. Y equals x cubed has a critical point at x equals 0, but there is no local max or min at x equals 0. What we do have, though, at x equals 0 for the graph of y equals x cubed is what we're calling and defining now an inflection point. All right, now the first question we're going to get to is how do we find inflection points? And we have to keep in mind our definition says a quantity or an inflection point comes from where the concavity changes or where the sign of the second derivative changes. Now, where might a quantity change signs? In other words, where could something go from positive to negative or negative to positive? Well, it could be where that quantity equals 0. 0 is the kind of dividing point between positive and negative values. All right, so if we're looking for inflection points, a good place to look is where the second derivative equals 0 or where the second derivative is undefined. Those are two possible spots where the concavity, the sign of the second derivative, can change. We're going to call these possible inflection points. The terminology, I like to use it, emphasizes that when the second derivative equals 0 or the second derivative is undefined at any of those x values, they might turn out to be inflection points, but they might not. Keep in mind your definition of an inflection point is a point where the concavity changes. So we're going to start looking for the intervals mentioned in the concavity test by looking for what we're going to call here possible inflection points. These are like critical points for the first derivative, but possible inflection points play the role for the second derivative. How we determine where the second derivative is positive or negative, how we find those intervals mentioned earlier in the concavity test, we're typically going to use a sign chart now for the second derivative. Hopefully you feel comfortable creating a sign chart for the first derivative. That was in our first part of this lecture. Definitely go back and review that. We're going to be looking at examples right now that are almost similar, but we're creating a sign chart for the second derivative. First derivative determines increasing, decreasing. Second derivative determines concavity. Let's go ahead and jump to a few examples. Continuing from our first part, we have now example 5. And let's take a look at 3 examples. The question asks, for each of these functions, find the intervals where it's concave up, the intervals where it's concave down, and any inflection points. Now, I'd like to give you an attempt to try this first, at least with part A. If you feel comfortable with creating a sign chart for the first derivative, try creating a sign chart here, but for the second derivative. Instead of using your critical points to give you the endpoints of those intervals, use what we call the possible inflection points, where the second derivative equals 0 or the second derivative is undefined. Try an attempt at part A. We'll go through that in a few minutes. Pause the video and we'll check in a few minutes. Welcome back. Let's go through part A. We have some short steps in red next to the various parts here. So since concavity deals with the second derivative, let's go ahead and just calculate first and second derivatives. That should be pretty straightforward here. Notice at the end, with the second derivative, we can simplify that by factoring out 12x. All right, now our second derivative is simplified. We factored it. It's going to make it very easy to find in step 2 the possible inflection points. Again, this is a polynomial. Polynomials are never undefined, so we can just worry about setting the second derivative equal to 0. And if we do that, since we already factored our second derivative, it's very easy to solve that Just set each factor to 0, and you should get two solutions, x equals 0 and x equals 2. These are what we're calling possible inflection points. We don't yet know that these actually are inflection points, since we haven't seen if the concavity changes at these x values, 0 and 2. That's going to be where our sign chart comes in. The sign chart is going to what tells us where the concavity changes from concave up to concave down, or vice versa. A positive second derivative means the graph is concave up. A negative second derivative means the graph is concave down. All right, we take our two possible inflection points. For the first derivative, we would have been using the critical points. We take x equals 0 and x equals 2, split the x-axis at those values, and we get three intervals, negative infinity to 0, 0 to 2, and 2 to infinity. And we can use our same tricks as before. We're going to pick a test point on each of those three intervals. We're going to choose going left to right, test points x equals -1, x equals 1, and then x equals 3. Again, you could choose any x values in those intervals. And since we have a simplified second derivative, it's factored, we can just determine the sign of each factor. So if you plug in your critical points, just look at the sign of each factor. Don't worry too much about getting the precise value of the second derivative. And you should find you get, going left to right, the signs of your second derivative should be positive, then negative, and then back to positive. Now what this sign chart tells us is any place there is a positive second derivative, the graph or the function will be concave up on that interval. So we find our function here is concave up on the intervals negative infinity to 0 and 2 to infinity. All right, the other part is where the second derivative is negative. That corresponds to an interval where the function is concave down, and there's a single interval there, the interval from 0 to 2, where our function is concave down. Now, if you take a look at your sign chart, notice at x equals 0, the concavity changes from concave up to concave down. You can see it in your sign chart. The second derivative is positive, and then the second derivative is negative. So there's a sign change in the second derivative at x equals 0, and the same thing happens at x equals 2. Again, the second derivative changes signs, now from negative to positive at x equals 2. And what that means is our two possible inflection points, both of them actually are inflection points. We have to use our sign chart to confirm that there is a change in the sign of the second derivative for us to say that there is an inflection point somewhere. All right, now with this one out of the way, maybe you want to now make an attempt or reattempt at parts B and C, and we'll check in a few minutes. Here's the derivatives to get you started for part B. Welcome back. Hopefully this one went well. This one is very simple to differentiate. We're just using the power rule. What makes this one as simple as possible is fully factoring your denominator. So you can first factor out in your second derivative 30x squared. And then the remaining part in parentheses, x squared minus 4, that can be factored further as a difference of squares, x minus 2 times x plus 2. So we fully factored our second derivative here. That's going to make it very easy to find our possible inflection points. Again, this is a polynomial expression, so we just have to worry about where the second derivative equals 0. Polynomials are never undefined. And since we have three factors, we can set all three of them equal to 0. since the right-hand side is 0. All right, and what we find here is each of those factors gives us 3 solutions for where the second derivative equals 0. We get a possible inflection point at x equals -2, another possible inflection point at x equals 0, and another possible inflection point at x equals 2. With these 3 x values, we can create a sign chart, and now with 3 x values, we always get one more interval. So we split our x-axis at -2, 0, and +2, and we get 4 intervals, -infinity to -2, -2 to 0, 0 to 2, and 2 to infinity. And it's the same thing. We can use our simplified second derivative, the fully factored version, to plug in test points to that and just worry about the sign of the second derivative. If you plug in the test points going left to right, -3, -1, +1, and +3, you should find in order the sign of your second derivative is positive, negative, notice a sign change, then negative, no sign change, and then back to positive, another sign change. Okay, our sign chart tells us everything for this question. The intervals where the graph or function is concave up or down, as well as where there are any inflection points. All right, the concave up intervals are pretty straightforward, -infinity to -2, and 2 to infinity. We have 2 intervals where the function is concave down, where the second derivative is negative, -2 to 0, and then 0 to 2. Now, if you check each of those possible inflection points, notice there is no change in sign of the second derivative at x equals 0. The second derivative is negative on both sides of 0, to the left and to the right. What that means is x equals 0 is not an inflection point. There is no change in the concavity at x equals 0. But there is a change in the concavity at x equals -2. Concavity goes from concave up to concave down, and at +2, the concavity also changes, now from concave down to concave up. All right, now out of 3 possible inflection points, we find this function only has 2 actual inflection points. So just keep that in mind while we're calling these possible inflection points. Not all of them might actually turn out to be inflection points. Our sign chart confirms that. All right, let's take a look at our last example, part C. Again, maybe pause the video to give this an attempt. Most of the work here is just in calculating and simplifying your first and second derivative. This one requires both the product rule and the chain rule. Pause the video and check in a few minutes. All right, welcome back. Let's go through our last part here, part C, before we move on. So hopefully you're comfortable calculating these derivatives using a combination of product and chain rule. The derivative of e to the -2x using the chain rule would be -2, the derivative of the inside, -2x, times e to the -2x. From the product rule, each factor or term contains an exponential in it, so you can factor that out, giving you a nice simplified first derivative, 1 minus 2x times e to the -2x. You're going to want to use the simplified first derivative to calculate the second derivative. Otherwise, in the unsimplified version of the first derivative, you'd have to use the product rule twice. All right, if you use the simplified first derivative, Again, use combination of product and chain rules to calculate the second derivative. Just be careful with that extra factor you get of the derivative of e to the negative 2x. You get another factor of negative 2. And if you distribute that negative 2 into the parentheses, 1 minus 2x, and combine it with the other, you should get, after you factor out the exponential, the remaining factor, 4x minus 4. That you can factor further or completely by factoring 4 out from each term, giving you this fully simplified second derivative, 4 times x minus 1 times e to the negative 2x. Again, very common for us to factor out exponentials in the various derivatives, like we've been encountering in lots of examples previously in the course. All right, this makes it very easy for us to find the possible inflection points. Again here, notice this combination of polynomials and exponentials will never be undefined, so we can jump straight to where the second derivative equals 0. And since we fully simplified our second derivative, it's very easy for us to solve this equation. We can ignore the exponential part, since we know exponentials never equal 0, and we can just jump straight to setting the part in parentheses, x minus 1 equal to 0, giving us a solution, a possible inflection point of x equals positive 1. With one possible inflection point, our sign chart for the second derivative is really simple. We just have one point at which we're splitting the x-axis, right at positive 1, and we get two intervals, negative infinity to 1, and the interval 1 to positive infinity. And if you pick test points x equals 0 and x equals 2, you should easily find using the simplified second derivative, and also remembering that exponentials are always positive. You get here the signs for your second derivative going left to right, negative and then positive. And what you can see in your sign chart here, there is a change in the concavity, a change in the sign of the second derivative. So x equals 1 is an inflection point. All right, our sign charts for the first and second derivative are going to be mostly what we use to get the graph of a function. We'll pull all this together in part 3, which is coming up after this. But for the remainder of this lecture, we have another test for critical points, but now coming from the second derivative. All right, let's go ahead and take a look at that. So we're going to go back to just taking a look at what a local minimum and a local maximum look like. And what we notice is a local min and local max each have a critical point. These correspond to a valley and a peak. Those are our basic way to get local maxes and local mins, although we can recall we could have sharp peaks and valleys, which would be where the derivative is undefined. We're going to ignore that here and just worry about these smooth, differentiable peaks and valleys, where the first derivative equals 0 for the local max and local min to give us a critical point. All right, now how do we tie this into what we're talking about now? What does the second derivative tell us? Well, let's keep in mind the second derivative tells us about concavity. And what we can see here is on the left, for the local minimum, that shape or graph is concave up. And then on the right there, the local maximum, that is a concave down shape. On the left, the concave up shape has a positive second derivative. On the right, the concave down shape has a negative second derivative. And what we get is a very nice test, what we now call the second derivative test. Just be careful with the terminology. First and second don't refer to sequence in which we arrived at them, but rather which order derivative is used in the test. The first derivative test applies to the first derivative of a function, and the second derivative test applies to the second derivative of a function. All right, what the test requires us to have first are critical points where the derivative equals 0. The second derivative test, as stated, doesn't apply to critical points where the first derivative is undefined. So just to be clear about that, we only worry about critical points coming from the first derivative equaling 0. All right, and we have a few conclusions here. Basically what we mentioned in our simple graphs above. If the second derivative evaluated at a critical point is positive, that means our graph is concave up. A concave up shape corresponds to a local minimum. The second part is if the second derivative evaluated at a critical point is negative, in other words, the graph is concave down, then that critical point corresponds to a local maximum. All right, so we have this nice correspondence, positive second derivative at a critical point, you get a local minimum, a negative second derivative, you get a local maximum at that critical point. Now there is a possibility that the second derivative at a critical point could equal 0. If that occurs, the second derivative test is inconclusive. In other words, there's no conclusion you can reach with the second derivative test. The critical point might be a local max, it might be a local min. The second derivative test just doesn't tell you that. In that case, you might want to go back and try the first derivative test to tell you about that critical point being a local maximum or local minimum. All right, so a summary here is that for the critical points, they get plugged into the second derivative. That's what f double prime of c means. We plug our critical points, c, into the second derivative, and then we check the sign of the second derivative. Now you might be wondering here with the second derivative test, if there is a possibility for it to be inconclusive, why would you want this? The first derivative test isn't inconclusive. It tells you when there is a local max, a local min, or if the critical point is neither. Well, as it turns out, as you move through the calculus sequence, it is the second derivative test that generalizes to multivariable calculus, Calc 3. So if you are moving on specifically to Calc 3, you'll see this second derivative test come back in a more complicated form when you deal with multivariable calculus. All right, let's take a look at one last final example just on applying the second derivative test. We call the local maximums and local minimums all together, those are referred to as local extrema. So the question here asks, find all local extrema, and I want you to do it using the second derivative test. So I'll give you a little bit of time to try this. Pause the video. What you want to look for first are critical points where the derivative equals 0, and then plug in each critical point into the second derivative and apply your various parts, the conclusions of the second derivative test to determine if each critical point is a local maximum or a local minimum. We'll check in a few minutes. All right, welcome back to our last example for this lecture. So our first step, which is a good one for kind of most problems at this point in the course, if you have no idea what to do, calculate the first and second derivative. All right, here that's fairly simple, just using the power rule. We can factor our first derivative and we can factor our second derivative. All right. The next step would be we want to find any critical points where the first derivative equals 0. So you can take your factored version for the first derivative, 4x squared times x minus 3, set that equal to 0, and we get two critical points, x equals 0 and x equals 3. Again, there is the possibility to get critical points from where the first derivative is undefined, but our second derivative test, as stated, doesn't apply to critical points where the first derivative is undefined, which doesn't actually happen here, but that's worthwhile to keep in mind. All right, now with each of these critical points where the first derivative equals 0, we can plug them into the second derivative and check the sign of the second derivative at each critical point. If you take your simplified second derivative, the factored version, and plug into there, you can get the signs very quickly. If you plug x equals 0 into your second derivative, you get that your second derivative just becomes 0. And if you plug x equals 3 into your second derivative, you should find that you get a positive sign for your second derivative. Now, what does the second derivative test tell us? Well, since the second derivative equals 0, the second derivative test is inconclusive. So in other words, x equals 0, we don't reach a conclusion from the second derivative test if x equals 0 is a local maximum or local minimum. X equals 3, however, does give us a conclusion or conclusive result. Since the second derivative is positive, notice I just drew a little concave up shape. Sometimes I have a hard time keeping track of what a positive second derivative or negative second derivative corresponds to. And you can see that little red parabola there, that's our basic shape for a concave up graph or curve. And that looks like a valley, a local min, which is one of the possibilities from the second derivative test. So we get a conclusion here, x equals 3 is a local minimum. Now what I would like you to do is apply the first derivative test to your critical point x equals 0, and what you'll find if you do that is there is no change in the sign of the first derivative at x equals 0. Create your sign chart for the first derivative. And since there's no change in sign at x equals 0 within the first derivative, that means x equals 0 is neither a local maximum or local minimum. All right, that wraps up part 2 of this lecture. So right now we're just focusing on what the second derivative tells us. In the next part, part 3 of this lecture, we'll pull this all together to sketch the graph of a function. Definitely make sure you thoroughly understand part 1 and part 2 before moving on to part 3, which comes next.